Greetings everybody. My name is Debendra Das Sharma. I'm with Intel. I'm here on behalf of Universal Chiplet Interconnect Express, UCIe. We'll talk about UCIe 2.0 specification, which is again advancing the chiplet ecosystem for on-package chiplet innovation. So here's the quick agenda, introduction, then we're going to talk about what's there in UCIe 2.0, an overview of that, then introduce about vertical chiplets with UCIe 3D, then talk about addressing some of the system in package challenges that we have through addressing, in general, DFX, design for testability, design for debug, those kind of things, and then talk a little bit about optional manageability features that we have with UCIe 2.0 and then do the conclusion. So we started UCIe in March of 2022 and there were 4 guiding principles. A lot of us have prior experience with driving very successful industry standards like PCI Express, CXL, USB. So these are based on the learnings over decades from those standards. And first thing is that, of course, you want to have an open chiplet ecosystem. You want it to be backward compatible so that people that have invested in something, it gets protected. People only change their designs if there is a need to change, not because other components in that you're connected to are making a change. So that's the same principle that applies, for example, in PCI Express and NVMe that you guys are all familiar with, right? It's the backwards compatibility. We need to deliver the best latency, the best power performance, all of those characteristics and cost metrics in order to be viable. If you don't deliver whatever is the best, people are going to come and innovate something else, right? So like any standard, you need to keep delivering to the best, what we call the KPIs, key performance indicators, and of course you have to continuously innovate to meet the needs of the evolving ecosystem. So this is the list of the board members. There are 12 board members who are 130 plus member companies, and pretty much these are the who's who in the area of semiconductors, packaging, foundry, IP, cloud service provider, pretty much everything from people that are going to do the design to people that are going to do the manufacturing to the end consumers, right, effectively. And this is the list of the set of the companies which keeps growing. So it's a very, less than, so about 3 years into the consortium and looking really good. So UCIe, this is the journey for UCIe. As I said earlier, March of 2022, we formed the consortium, we announced it, UCIe 1.0 specification got released. That was donated by Intel, my employer. So that was a full specification. We incorporated in June and at that point, UCIe 1.2 belongs to the consortium, right? Once you donate it, it belongs to the industry body. June of 2022, we incorporated the consortium, so it becomes a legal entity. And then August 2023, which was last year, we released 1.1 specification. And that basically was more or less whatever was there in 1.0. We added a few things around automotive, we added a few things around some optimizations and some compliance tests. That's basically what was there. And basically UCIe 1.0 and 1.1 are what I call planar interconnects. So what it means is that you have chiplets that are connected, they're side by side and you connect them through a planar interconnect, okay? We announced 2.0, which is what I'm going to talk about, in August of this year. So that has a bunch of enhancements on top of 1.0 for planar as well as the other thing that we have done, which is the vertical interconnect with UCIe 2.0. So that's new. The vertical connections is new. There are 5 working groups in UCIe Consortium: electrical, protocol, form factor compliance, manageability, security, and systems and software. So these work groups work on the technical aspects of the specification. There are also a couple of horizontal work groups. Automotive, it collects all the needs of the automotive segment and feeds into these as needed. And then there's a marketing work group that's responsible for the outreach. So let's see, what's there in UCIe 2.0. As I said earlier, UCIe 1.0 and 1.1 was all about planar interconnects. So 2.0 moved to 3D. So of course will continue to support the planar interconnects, but the 3D connections is what gets introduced with UCIe 2.0. And we looked at holistically, and we'll talk more about that, support for manageability debug testing for any kind of a SIP construction with multiple chiplets, some optimizations, and of course we are fully backward compatible with the prior generations of the specification. So 3D, it's basically, as I said, 1.0, 1.1 was two-dimensional, and then 2.0 is three-dimensional, right? So two-dimensional is side-by-side connectivity. You connect them through an interconnect here on the package. 3D is you connect them vertically. And of course, side-by-side will also exist using 2D, but the vertical interconnection is what 3D is about. There are a few things that are driving 3D, and that has to do with the underlying technologies. So there is a technology called hybrid bonding. So what it does is it enables you to connect things at the metal layer effectively between the two chiplets, adjacent chiplets, and the bump pitches are fairly small. So we see technology that are 10 micron going down to sub-micron, and I'll talk about why that's beneficial. And although, for people that still want to be with the micro bumps, which is what you provide, in general, you are going to, 2D is all about bumps and micro bumps at the bottom of the die. You can still connect them using micro bumps, and that's 10 to 25 micron. That's supported even in the vertical one. But the optimization point are for the micro bumps here. What it does is the thing about reducing of the bump pitches doesn't matter whether it is hybrid bonding or bumps or micro bumps. If you reduce the bump pitch, number of wires grows inverse to the square of the bump pitch reduction. And by that what I mean is, let's say if you have 25 micron bump pitch, now you go down to 5 micron. So what you have done is that you have done a 5x reduction in the bump pitch. But the number of wires goes up as 25x because it's going in both the dimensions, right? So you're going to pack more, right? So that's one benefit that you get, which is from 3D. 3D is more, more amenable to much more reduced bump pitches. So you're going to get more number of wires. There is another aspect of 3D that really helps, which is that if you think about a 2D chiplet, right? You basically have to come to the edge of the die to connect to the next one. So you're going to basically come to what we call the soar line of the die, and you're going to consume the soar line area, the soar line length in order to make the connection to the neighboring die. So you're soar line limited, whereas with 3D, you don't need to go to the edge of the die. You can connect to your neighboring die in place wherever you need. So in other words, if I have something over here in the middle of the chip that I need to connect to the middle of the chip on the other side, I just connect it directly. I don't have to go to the edge of the die. So now instead of taking everything to the edge and consuming the area there along the soar line, you can connect them in place. So you get the entire area of the chiplet available to you. Plus you get the benefit of the reduction in the bump pitch, right? So these are the dual benefits, and they really add up very, very, very significantly to the amount of bandwidth that you are going to get. The other thing that happens with 3D is because these are fused together effectively at the metal layer, the interconnect distance is practically zero. 2D, you are going to still have the distance, even though it's better than, let's say, PCI Express, where you are going across the board, right? In 2D, let's say just pure 2D, you can go up to 25 millimeter on the package. If it is 2.5D with the advanced packaging technology, it is still 2 millimeter. Here it is practically zero. And even if you go from the back of the chiplet to the front, it still is tens of microns. So distance goes down. You have a lot more wires basically. So fundamentally what you need to do is, you just need to think about how do I reduce my power? How do you reduce power? You keep things really, really simple. You don't run things fast, you run things really slow at the SOC frequency. And that's how we get the benefit. So what you see a picture here, and that is showing here, two chiplets. There are 9 what we call NOCs, network on chip controller, right? I mean, effectively all chips have some form of a, network on chip NOC controller, and then, it gets connected in a 2D fashion. You just connect them to the neighboring chiplet, right? And this shows the picture here, which is saying that the NOC just directly talks to the PHY, and the PHY is nothing but we'll see a very simple, inverter, that's it. Because you are basically running this link at SOC frequency. No fancy serializer, deserializer, nothing. Just send the signal across as you would on the die. So with this, there are 3 columns here that I'll talk about 2D, 2.5D, and 3D. And these are the data rates. As you can see, these have higher data rates for the 2-dimensional or the planar interconnects. But 3D, it's up to 4. You just run at the SOC frequency. These are the widths, and widths can be anything. You can just have multiple links connected, right, if you need more bandwidth. That's the basic unit. Basically, what we do is that we choose a unit that is at the sweet spot in terms of clock distribution and everything else, because you have to also send a forwarded clock with every width. So you choose the most wires that you can, but not overwhelm your clocking tree and all of those. These are the bump pitches. 2D is 100 to 130 micron, 2.5D is 25 to 55, and 3D, as I talked about earlier, less than 10 is what we're optimized for, but we can go 10 to 25. It's not the best, but you're going to still work. Channel reach, again, it's 3D vertical. Now, if you look into the key metrics here, so bandwidth, so there are 2 things. Bandwidth in terms of bandwidth on source line, which is gigabytes per second per millimeter, and then the bandwidth density, which is how much area it consumes, gigabyte per second per square millimeter. So both are important. So you'll see that there are a set of numbers here for 2D, 2.5D, and basically what it means is, let's say if I pick this number here, 188, it means that if you're in this 2.5D, you run your link at 4 gig, 64 wires, they're going to give you 188 gigabytes per second running at 4 gig. If you run at 8 gig, you're going to get 376 gigabytes per second per square millimeter, and so on and so forth. If you run at 32 gig, you are going to get 1350. And these numbers are for the 2.5D at 45 micron. Clearly, if you go down to 25, these numbers will go up because of the square rule. Now, here we give a range of numbers, and you will see that bandwidth per source line, we just say it is NA because it is vertical, right? I mean, you can always say I consume 0 length on the source line. So if I divide something by 0, I get infinite. So we just say NA instead of putting infinity there. If you look into the bandwidth density, at 9 micron, we are 4,000 gigabytes per second per square millimeter, assuming 4 gig operating frequency. 4,000, so which is 4 terabytes per second at 9 micron, and then you go to 5 micron, you are going to be 12 terabytes per second per square millimeter, and this takes into account all the things like as your bump pitches increase, you have to have more power and ground, so it derates it appropriately. And by the time you're at 1 micron, you are at 300 terabytes per second per square millimeter. So clearly, bandwidth is not a problem. You got an abundance of bandwidth, so that's a good problem to have. Okay, we are not going to be in short supply of bandwidth. You just route less wires, right? It doesn't mean that you have to route for the entire chiplet, right? Power efficiency number wise, and by the way, what is it on the external interconnect? Like if you are doing PCI Express, doing NVMe, or doing Ethernet, these numbers are in a good day they are double digit gigabytes per second per square millimeter, definitely less than 3 digits, okay? So you're getting an order of magnitude improvement with 2D, 2.5D at least, maybe 2 orders of magnitude, and then by the time you are hitting here, you are getting another 2 to 3 orders of magnitude better bandwidth density than 2.5D, which in itself is an order or 2 magnitude better than external. So, which is again what you would expect because these are very short distances, very simple circuits. Power efficiency target wise, 0.5 picojoule per bit, 0.25 picojoule per bit, and somewhere between 0.05. By the time we hit 1 micron, we think we will be at 0.01 picojoule per bit. So external interconnects are 5 to 10 picojoule per bit. PCI Express, Ethernet, which is again what you would expect because you're traveling the longer distance, so you need to burn more power, more complicated circuitry, all of that. So you get an order of magnitude improvement here, and by the time you hit the 3D, you are yet another order or 2 magnitude better, which is what you would expect because at the end of the day, you want these to really look like whatever is there on the die. On the die, even to transfer a bit from one knock to the other knock, if your knock size is like 2 to 3 millimeter, you will end up consuming about 0.15 picojoule per bit, because you need to still flop to 2 to 3 stages at 4 gigahertz, for example. So it's a vast. In fact, by doing 3D, what happens is your net distance reduces. You get more bandwidth and you end up with better performance. Of course, 3D has its own challenges, manufacturing challenges and all of that, but at least the overall key performance metrics will improve significantly with 3D. Low power entry exit. These numbers were fairly low to begin with. Here it is 0, because I can really, if I don't send my clock, I just don't send my data. It's as simple as that. I just save on the power. Even here it is pretty good. 0.5 to 1 nanosecond, that's hardly anything. You can turn things off and on very quickly. External interconnects, it takes us multiple microseconds because those circuits take longer to train, right? They take a long time to turn off, and once you have turned them off, you have to spend many, many microseconds to retrain the circuits. Here, none of those are there. So what it really does is, if I consume, let's say, if I have an intermittent consumption of bandwidth, I can turn these things on and off. Let's say I consume 10% of the bandwidth because every 10th cycle I have something to send. I consume about 10% of the power. Peak power, and once that granularity is not there, it's very hard to get that kind of power savings in an external interconnect. We measure reliability in FIT. FIT is basically failure in time, how many failures you get in a billion hours, and that number is significantly less than 1. And your normal chips by themselves have 3 to 4 digit of FIT number. So contribution of the interconnect should be practically 0, which it is. So overall, really good set of KPIs there from the 3D. Now let's switch gears and talk about something different, which is around the design for manageability, test, debug, telemetry, all of those things. If you look at UCIe 1.0 and 1.1, we had a lot of these things already built in, but those were at the interconnect level. In other words, we had things like loopback, we had things like margining, all of those things that help you establish whether this link is working or not, right? And if something fails, like you've got error reporting, all of those were there. Here what we are doing is we are taking a step back and saying that that's not enough, because once people really connect things, they want to make sure that they have IPs from a bunch of sources, they have got chiplets from a bunch of sources. Things are not just limited to the interconnect at the chiplet level. So for example, if you look into this chiplet, right, I mean, you can have different types of package pins, like, those can be PCI Express, USB, whatever, right? Ethernet, all of those things. How do I test something like this? How do I debug if there is a failure here between the two chiplets? They may or may not be related to UCIe, but nevertheless, you are putting them on a package. How do you debug them? You can't put a logic analyzer there. You can't put a scope in there, right? So, we basically said that we need to look at this thing and we need to be able to work with all the other external interfaces that are there by building some kind of a bridge function, but define things at a chiplet level, at a package level, some kind of a infrastructure that will help people accomplish all of these goals. And we basically have the same common infrastructure for all of this, even though they are unrelated, like test is different than debug, is different than telemetry, but you will see that we have used the same kind of the infrastructure. So that way, you're not building different infrastructure for different things. And the other thing that we did was, for example, right, if I want to debug something that's going on here, well, you can send debug signals over either the same UCIe link by time multiplexing, or you can have a dedicated set of UCIe pins if you want, maybe just the sideband, which is 4 pins. Use that sideband, that's 800 megabit per second of bandwidth, and that should be able to, you should be able to take all of those and then dump it out on maybe a PCI Express set of pins outside. So those are the types of things that we are accomplishing with 2.0, and there is a list of how much of bandwidth is available here so that we give people guidance, right? So not all chiplets have the same demand. Some require very high, for example, scan chain, right? If you ask people, different chiplets will say, I have different needs for different scan chain bandwidth, right? It can be very low to something very high in gigabits per second kind of number. So it's not a one size fits all. So fundamentally, it's a debug architecture is a hub and spoke model. There is this notion of a management bridge. There is the notion of a management director, which is the root of trust for the whole package. It basically makes sure that there is no security holes, all of those things, everything gets through that. And then there is a hub in each chiplet, and then there are multiple spokes. So for example, this hub controls all the spokes within the chiplet and also controls communication to the neighboring chiplet. That happens. And the spoke can be a MEM-based, which is not related to UCIe. It can be a telemetry thing, again, not related to UCIe, but you basically go through the same infrastructure. And we are not telling people how to do it. Everybody has some mechanism. All that we are doing is providing you with a common set of architectural construct, like think of it like a wrapper, like like PCI Express has, right? Like a header file that tells you what type it is, and then within that you have got your own set of definitions. So then software looks at it and says, oh, I know this. This is the telemetry of this particular supplier, and I know how to use it, right? That's all that it is doing. And then how do you send the bits across on UCIe? It's basically how do you package the bits and then send them across. So that's all it's doing, and defining how does an interface with an external link work like, right? So once you have all of these pieces together, now you can stitch things and you can make them work seamlessly. So that's the idea. There is a white paper that we have. You can take a look, and we are doing a public webinar tomorrow also. If you want, we are going to go through this in quite a bit of detail. So in summary, everything is a journey, like a PCI Express, CXL, NVMe. All of these have been like a multi-decade, multi-generation journey. Chiplets are just starting. And as you can see, we are on a very healthy cadence in terms of, and these things are coming not because people are bored, they want to invent something, but because there is a real need, right? A lot of companies are investing a lot of time and resources. So join us if you have not done so. And thank you. Any quick questions?
So the bit rate that you showed?
Yeah.
How do I relate that to other bit rates to know if that's, it's obviously an extremely small number, but how do I put that in the proper context?
Let's see here. This one, right? Yeah. So if you look into this bit rate here, so you got 4 gigabit per second, 80 lanes. So that's 320 gigabit per second.
Go ahead. Actually, I meant to say bit error rate. But go ahead.
Oh, bit error rate. Sure. Yeah. Okay. Bit error rate is 10 to the power minus 27. Right. So how do you put that in context, right? PCI Express bit error rate is 10 to the power minus 12.
Okay.
Are we being overly conservative here? The answer is, meaning to some extent, yes, but not too much. There, I got a 64-bit CRC to protect things, so that gives me a lot of coverage. Here, I don't want to really invest on a 64-bit CRC. These are the things where I'm just doing the bare minimum. I basically look into, hey, I want to send 100 terabits per second, and what bit rate do I really need so that I don't need any. People in general will have their own internal ECC, but I'm not really relying on that, right? What do I really need to get away without doing any of this forward error correction or CRC or any of that fancy stuff, right? So, and at these lower data rates, it's very achievable. If you look at even these data rates, like 24 and 32, by the time we are here, we do need CRC, by the way. It's too hard to give the entire table here, but it's 10 to the power minus 15 there. So, yeah, the way to look at this is that my reliability fit, I start with less than 1. In general, I look for 10 to the power minus 3. Even though I say less than 1, I do a calculation with minus 3 at least, and then back up from there and go to my bit error rate. And then I have a fixed bandwidth number, right? I overshoot on the bandwidth side saying, this chip to this chip, I will need X amount of bandwidth. So then back calculate. Good question. Any other questions? All right. Hey, thank you very much.